All right, guys, welcome back. We are now moving into our next topic in ENCOR, which is external BGP. We don't really talk too much about internal BGP in this class. Number one, internal BGP is not typically used in most enterprises because we would rely on some sort of interior gateway protocol to route internally within our organization. So we talk about external BGP pairing relationships, but when we get into the advanced routing course, we'll most likely talk about internal BGP as well, because there are some kind of unique differences between external BGP and internal BGP. So that is definitely something that we will probably want to talk about at some point in the near future. BGP as a protocol is really completely different than any other routing protocol that you learn about in any kind of advanced routing course. BGP is an application layer protocol. It runs over TCP as opposed to running over the IP layer directly. So it uses things like TCP keep alives, the three-way handshake to establish an adjacency, etc., to initially establish those adjacencies. And then overall, the protocol itself is kind of just completely different. We define it as a path vector routing protocol as opposed to distance vector or link state because it uses various BGP path attributes. And we'll pull up, there's a great Cisco document that talks about the BGP Path Selection algorithm and how it works. And then in addition, all those videos that I provided you guys for the CCIE mentorship program, tons and tons of great BGP information in those lessons as well. In fact, I think there's over 10 separate videos on BGP alone. So it is a pretty robust routing protocol. We typically will see the use of external BGP when we're connecting to a service provider, especially when we have a dual-homed or multi-homed service provider configuration. And with IPv6, we may even be acting as our own service provider, offering our own prefixes to the internet and housing our own prefixes. So in that case, we might even have a publicly registered BGP autonomous system number, and we're actually acting as a service provider for those particular prefixes out to the rest of the world. One of the things you might see with BGP as well, it's very rare, but especially for a kind of a standard client, is you might see a BGP host operating as what we refer to as a transit AS, or a transit autonomous system for the internet. So it's an interesting protocol. I don't know how much in depth we're going to go into it in this particular set of lessons here, but we will spend a little bit of time on this protocol, and then we'll move into some of the other topics later today. So BGP is a routing protocol. It is used to exchange network layer reachability information, or what we call NLRI, between autonomous systems. And just like we saw with OSPF and just like we saw with the eIGRP, an autonomous system is a collection of networks under a single administrative domain. In the case of BGP, though, especially when it comes to routing, just like we talked about with OSPF, where routing was about routing to nodes and not to individual networks or prefixes, in the case of BGP, routing is about routing to autonomous systems. And we kind of think of autonomous systems as hops, if you will. Notice the cloud on the left, AS 65000, that is running internal protocols, an internal IGP like OSPF or eIGRP. On the right, we have AS 65001. That's running an internal IGP routing protocol like OSPF and eIGRP. And then the exterior gateway protocol that we're running, don't confuse that with the legacy eBGP protocol. There used to be a protocol, in fact, it was the very, very first routing protocol that was ever invented, called the exterior gateway protocol. But in this case, we're just using that term loosely to describe the autonomous system routing, is BGP, the Border Gateway Protocol. And what makes this an exterior protocol, or what makes this an eBGP scenario, is that we have peering relationships between two different autonomous system numbers. If we were peering two BGP speakers, and by the way, that's what a BGP router is referred to as, a BGP speaker. If we were peering two BGP speakers that were So I don't know what happened with my audio. My microphone died, so hopefully we didn't miss too much of that audio. But we're just kind of doing this introduction. I know you guys online heard everything I said because I was using a different microphone for that. But there's a lot of characteristics of BGP that make it unique, right? It is a path vector protocol, and we use what we call path vector attributes to make decisions on how we're going to route to a particular destination. Reachability is autonomous system to autonomous system. So oftentimes, a lot of people will kind of classify BGP as a distance vector protocol because it kind of looks like a distance vector protocol. You know how many autonomous systems exist. Let's say I'm going from 65010 to some prefix 192.168.24.0 and 65050. I know about the autonomous systems in between. So I know I could go from 65010 to 65020 to 65040 to 30 and then to 50. That is what we refer to as an Aas Path attribute, an autonomous system path attribute. What I don't know from a BGP perspective, though, is what's inside of those autonomous systems. I don't know how many routers existed within those autonomous systems. I don't know, what kind of IGP protocols running in those systems. So as far as visibility goes, we have very little visibility outside of our own autonomous system on what's happening within each of those other autonomous systems, which is kind of an interesting concept, right? But Aas Path is what BGP is concerned with. So I would probably choose to go from 10 to 20 to 30 to 50 rather than go from 10 to 20 to 40 to 30 to 50 because the Aas Path is shorter. And again, we're not taking into account bandwidth. We're not taking into account speed. We're taking into account basically the number of hops, which in this case, a hop would be considered an autonomous system. That is actually one of the primary components of the BGP decision tree is Aas Path. Weight is the first one, local preference is the second one, Aas Path is the third one, and so on. We'll take a look at that. If the book doesn't get into that in detail, I'll quickly go through a document that I've created for one of my other classes, just to kind of give you an idea of these attributes. Some of them are well known, mandatory attributes, which means you have to understand them and you have to use them, like Aas Path. Some of them are well known discretionary attributes, so every BGP implementation understands the attribute, but it's to your discretion if you want to use that attribute or not to make a policy decision. And then you have transitive and non-transitive attributes, and so on. So there's just a whole bunch of different kind of ways that we define the policy decisions that BGP makes. The path vector information includes a list of complete hop-by-hop paths of BGP autonomous system numbers that are necessary to reach a particular destination. And the networks that are reachable at the end of the path would be what we're actually trying to get to. So we are routing to destination prefixes. We're just using policies and BGP attributes to make those routing decisions rather than a traditional or conventional metric to make those routing decisions. All right. The Aas Path information is useful to create this graph of a loop-free topology. Just like we talked about with traditional distance vector protocols, we like to have a loop-free topology. And we can define policies on how data is going to flow through different autonomous systems. Some of the attributes that we have in BGP are going to influence outbound routing policies. In fact, most of them influence how we leave the autonomous system. And some attributes will identify how we enter an autonomous system. In other words, we can kind of influence how a peer might decide to come into our autonomous system. Most of those attributes are going to be discretionary attributes, right? We technically really can't control how somebody decides to route out of their own autonomous system, but we can suggest how we'd like them to route. Maybe we have two different ways of reaching a neighboring AS, and we're suggesting we want you to come this way as opposed to that way. Generally speaking, most providers will honor that code, if you will, and say, hey, if you're suggesting how you want me to route, I'll take that suggestion to heart and I'll go ahead and do that. One of the specific attributes that we use to do that is called a multi-exit discriminator value. And we'll talk about that later on. All right. So BGP allows you to define a routing policy decision at the autonomous system level. These policies can be implemented for all networks that are owned within that autonomous system or for a certain classless interdomain routing block of networks or prefixes. So we have complete granularity on how we can apply these attributes. I can say for certain prefixes, I want to route this way. For other prefixes, I want to route this way, and so on. All right. BGP specifies that a router can advertise to neighboring autonomous systems only those routes that it uses itself. That's very much a distance vector concept, isn't it? In EIGRP, it's the exact same concept. I only advertise the routes to my peers that I'm using. I don't advertise every possible choice, unlike a link state routing protocol. I advertise the routes that I'm using. That's why a lot of times people will tend to classify BGP as kind of a distance vector type of routing protocol. The hop-by-hop routing paradigm does not support all possible policies. For example, BGP does not enable one AS to send traffic to a neighboring AS, intending that traffic to take a different route from the path that is taken by traffic that originates in that neighboring AS. That sounds very confusing, but basically what they're saying is, look, I can control how traffic leaves my autonomous system. I have complete autonomy and complete control on the policy decisions that I'm using to make routing decisions outside of my autonomous system. I can suggest, even though it's mostly discretionary, I could suggest how you route to my autonomous system. However, I cannot influence how you decide to route within your autonomous system beyond my AS on to other autonomous systems. So once I send my traffic to you, you're making independent policy decisions on how you route, separate from whatever decisions I would have made. All right? In other words, I cannot influence how traffic in a neighboring AS gets routed. All right? Now, BGP does support policies that conform to this hop-by-hop routing design, and that's where we get into the whole concept of well-known attributes versus not well-known attributes, and discretionary versus mandatory, and so on. There are a certain set of attributes that everybody kind of adheres to. Aas Path, for example, is one of those attributes. Wait, not one of those attributes. Wait is a Cisco proprietary attribute. Local preference is a well-known mandatory attribute. But local preference only affects how you decide to leave your autonomous system. So that's one of the challenging things with BGP is just like kind of what we did with OSPF, where we went through all the different link state advertisement types, and we talked about the link state database and who generates what types of LSAs and how that influences our node routing decisions and so on. In BGP, we have specific attributes that we have to learn. Lots and lots of different attributes that we have to learn specifically for BGP. Okay, so what are our overall objectives for BGP? We want to make sure that we can scale well. We want to make sure that we can exchange routing information securely. So authentication could be something that we decide to implement. Certainly, filtering is a very important concept. And that's where route maps come in. Route maps are used quite heavily in BGP to define how we decide to filter routes leaving the autonomous system and routes coming into the autonomous system, and how we affect policy decisions. A lot of times we'll use route maps to set these values that I'm referencing, local preference and weight and Aas Path and so on. The support for routing policies. Routing between autonomous systems might not always follow the optimal path. And so we have policies that specifically identify outgoing and incoming traffic flows. All right? So all kinds of interesting concepts with BGP. Even though we'll probably see it again later on, as part of this discussion here, I'm going to kind of start to go over some of those policy decisions, and because it doesn't hurt to see them more than once. So I'm going to probably pull up this document here in a minute and kind of go through it with you guys. So I'm not going to go through the details here, but basically what they're saying is, look, one of the policy decisions that BGP permits me to choose from, and it is actually one of the most important policy decisions overall, is Aas Path. Aas Path is a well-known mandatory attribute. Now we can trick it. We can do things like Aas Path Prepending or Aas Path filters to modify how routing is done. But Aas Path is a very, very common way of deciding how we're going to reach a particular destination. And it is literally, we're creating a list, if you will, of the autonomous system numbers that I have to go through to reach a particular prefix. So it might be 10 to 20 to 30 to 60. It might be 10 to 40 to 50 to 60. It might be 10 to 20 to 50 to 60. It might be 10 to 40 to 50 to 30 to 60, whatever it might be. And again, generally speaking, the shortest Aas path is the one that we're going to choose. But that's not always the case. We can, the shortest Aas path is definitely one of the top attributes that's chosen. In fact, it's the third attribute in the list, and weight and local preference are generally left to their default values. So Aas Path kind of becomes the first attribute that we look at to make a policy routing decision. But the Aas Path can be manipulated. We can inject fake hops, if you will, in that path to make the path appear to be longer, and so on. And so there's a lot of ways that we can influence policy routing based on manipulating those values. All right, so they kind of go through a breakdown of the different paths that we can choose and so on. I'm not going to read all this, but you get the general idea. Which statement best describes an autonomous system? An AS is a collection of networks under a single administrative domain. Well, that's pretty much it. We don't have to really go any further. It's one single administrative domain. All right. AS numbers are not 0 to 255. AS requires an IGP protocol to exchange routing information between another AS is an EGP, not an IGP. AS is a collection of networks that belong to different enterprise networks, would be the opposite of what it is. So I've got some notes here that I took when I was recording some lessons in my CCIE program, and I kind of wanted to go through these really quickly, just really bullet point by bullet point, to give you some additional information that I think will be very useful. We'll probably see some of this again as we go through some of the other sections here. BGP is an open standards-based protocol, and I'm just kind of going to read this because it's pretty concise the way it's written anyway, so it's kind of difficult to summarize what's already here. It is a path vector protocol. It is exterior, like we talked about. The base RFC 4271, and it says here, as a path vector routing protocol, we use prefix attributes to make routing decisions. There are 13 core decisions, which is pretty extensive, that we make. The attributes apply to the prefix, so we apply attributes on a per prefix basis and not the links themselves. So much like a distance vector routing protocol, it's about the prefixes, it's not about the links. What are the use cases for BGP? We use BGP to route between external ASs. That's what we were talking about in our lesson. if I have a large data center, if I'm trying to scale DMVPNs and I want to establish kind of a BGP design, I can do it that way. It is an extensible and scalable protocol. This is a little bit beyond the scope of what we're talking about in this class, but address family identifiers, much like we saw with the EIGRP named mode configuration or OSPF-v3, we can set up BGP with address families. We can also do sub-address families. Over 800,000 prefixes in the global routing table for IPv4 and over 70,000 v6 prefixes. When should we not use BGP? We should not use BGP as a traditional routing protocol. I've heard, very rarely, but I've heard from a couple of students in the past that they tried to use BGP as an internal routing protocol. It's not designed for that. Yes, you could theoretically use BGP to exchange reachability information inside your organization, but the protocol is not efficient enough for that. It's very slow. Topology change propagation takes forever, but that's by design, right? BGP was designed to be a slow protocol. And yes, it scales well from the perspective of the size of the databases, but it doesn't really scale well in an overall design, from a design perspective, especially within an autonomous system. It is an application, like we said, that runs on top of TCP, port 179, to exchange network layer reachability information. BGP is a reachability protocol, not really a routing protocol. Okay? That's a concept that a lot of people don't really understand. BGP is always kind of classified as a routing protocol, but it is not really a routing protocol. BGP has no visibility of the topology. We talked about that. It is solely used to route from AS to AS. We don't really know what's happening within the AS itself. All right. Now, if I wanted to use BGP in a public sense, there's two ways that we can get public prefixes from a provider. I can get provider assigned prefixes where the service provider owns the prefix space and they dictate the global policy on how those prefixes are routed. In our case, most likely BGP is not necessary. What am I going to use to connect to provider assigned address blocks? I'm going to use a default route to the internet, and I'm going to use some sort of IGP internally to route internally, and then I'll have some sort of NAT boundary on the perimeter to convert to those publicly routable addresses. Or I can be my own service provider. I can go out and register my own ASN. I can go out and register my own global prefixes, but that means that I become the service provider for those prefixes, and I have to define the policy for routing to those prefixes. That's a lot less common, but it does exist. All right. There is some documentation. BGP Best Path Selection algorithm. That's a really, really good document to read. It's on cisco.com. I actually have most of that here. We'll talk about that in a minute. Internet Routing Architectures. That's a Cisco Press book. Routing for TCP/IP Volume 2. Practical BGP and Optimal Routing Design. These are all available on Amazon. More than just BGP, but these are really, really good books that discuss BGP quite a bit. Like I said before, every single routing protocol has three things that we concern ourselves with, right? And I've mentioned this multiple times throughout the lessons that we've had, but three things that we concern ourselves with. What are the messages that we use in the protocol to exchange and disseminate information? What are the data structures that we use to house the information and to store the information that we've collected? And then what is the algorithm that we use to make decisions, right? Well, in BGP, it's a path vector algorithm. We don't really have a name for it specifically, like Dijkstra's or Dual or the Bellman-Ford algorithm. But it is those 13 core decisions. There's actually more than that, but there's some tiebreakers. But 13 core decisions. That's the BGP Path Attribute algorithm that we talk about. But the message types, right? We have the BGP header, which has a marker, a length, and a type field. We have, oops, I skipped a section there. Sorry, BGP message types, open message, right? These are used to exchange things like what are the BGP peers capable of, what is the autonomous system number, what is the peering information, etc. And those open messages are sent after a three-way handshake gets established or allows us to establish a TCP session between the peers. We have keep alives. We have an update, which would obviously be used to send out routing information. We have notifications, which are used to send out messages that indicate that an error has occurred. Maybe it's an error with exchanging information or an error with peering or whatever. We don't really want to see notifications. Route refresh is kind of a message type. It's a way for us to do kind of what we call a soft reset on a peer, so that we don't have to tear down the TCP session and reestablish it and kind of go through the whole process of exchanging information. When you make policy changes in BGP and you apply those policy changes to prefixes, those policy changes don't get propagated unless the peering relationship is reset, either soft reset or hard reset. So that's why we have that route refresh to allow us to propagate policy change information between BGP speakers. Message format, we don't really need to get into right now. Some different BGP states. Idle state. This is the beginning of the BGP process. So if you see you're doing a debug, or you're seeing you're debugging the BGP session establishment process, idle is not good because we're kind of just starting the BGP process. Connect is a BGP speaker is waiting. That should be say waiting. Waiting for the TCP connection to be completed. So we've got maybe a SYN, but we haven't received the SYN ACK or the ACK. Active means we're trying to initiate a TCP connection. So we maybe sent a SYN, but we haven't gotten a SYN ACK back. Open sent, where we've sent an open message to establish a session with the peer, but we haven't heard anything back. Open confirm, and finally established, right? So unlike OSPF, where we got down, init, two-way XStart exchange loading full, in BGP, we're pretty much, all these other states are transitional states. We pretty much go from idle to established, right? There's no state that in the middle that you should see or you should be kind of stuck in a normal operation. All right. We talked a little bit about the autonomous system number as well. Originally a 2-byte value. Public AS was 1 through 64.511. Private AS 64.512 to 65.535. New implementations, we have a 4-byte field, which is 32 bits as opposed to 16 bits. And it's just basically 0 to 65,535 twice, separated with a dot. It just gives us a lot more ASNs to choose from. Now, what about these attributes? We've mentioned a few times that BGP is a policy routing, a policy-based protocol, right? We're using BGP attributes to decide how we want to communicate reachability information between the peers, all right? We use type linked value fields. We talked about what attributes type linked values are, those Tupperware containers, if you will, kind of generic containers to carry information. Type is what type of container is it? Length is how large the container is, and the value is what's contained within the container. So TLVs are used in EIGRP, they're used in BGP to carry information. Every attribute is 2 bytes. 1 byte is for flags, the other byte is for the attribute details. All right? Optional and well-known, right? So a well-known attribute is an attribute that everybody understands in BGP. Aas Path, origin, next hop, these are well-known attributes. All right, well-known mandatory attribute. All BGP speakers have to understand what that attribute is, and all BGP speakers must provide information about that attribute in their policy decisions and their policy updates. Aas Path is a well-known mandatory attribute. Several attributes actually are well-known mandatory. Most of the primary attributes that we use to make policy decisions are well-known mandatory. A well-known discretionary attribute is an attribute that every BGP speaker must understand, but not every BGP speaker needs to use these attributes. All right. So, an example of that would be a multi-exit discriminator. Actually, that's more of an optional non-transitive attribute, but atomic aggregate would be an example of a well-known discretionary attribute, meaning that it is defined within every implementation of BGP. You can choose to ignore that attribute. You can choose to accept that attribute. You can choose to use that attribute in your policy decision or not. Optional BGP attribute types. We have optional transitive and optional non-transitive. Optional basically means that the BGP speaker may or may not understand this attribute. It may not be implemented within their version of BGP. All right. Transitive means it's an attribute that gets passed on from one autonomous system to another. Non-transitive is an attribute that does not get passed from one AS to another. All right. So these are the attributes, and I suppose I could kind of go through all these. You can see that there are 16 different actual type codes for BGP attributes. Origin is a well-known mandatory attribute. Aas Path, well-known mandatory. Next hop, well-known mandatory. So these three attributes you will always see tied to, like if you did a show IP BGP, for example, you're always going to see these attributes listed in the topology database because they're well known and they're mandatory. Multi-exit discriminator is optional non-transitive. Now, that means that it doesn't get passed beyond the next autonomous system. However, it does get passed from one autonomous system to the next. Let me explain what I mean by that. Just because it's non-transitive doesn't mean that I can't send you the information. Non-transitive means if I send you this information and I'm in AS1 and you're in AS2, and I send you this information, it stops at you. It doesn't get sent on to AS3 or AS4 or AS5. Transitive would mean that that attribute would get propagated beyond the peering AS, and it would be sent on down the line to other ASs along the path. Local preference is a well-known discretionary attribute, meaning that you can choose to ignore it or you can choose to use it, but everybody knows that it exists. Atomic aggregate, also well-known discretionary. Aggregator, optional transitive. Community, optional transitive. Originator ID, optional non-transitive. Cluster list, optional non-transitive, and so on. I don't know that it's within the scope of this particular class to understand what every single one of these attributes does. And in fact, I don't think it is. There are certain attributes that you should definitely be versed on. Certainly the well-known mandatory attributes, I would say that those would be the ones that you focus a lot of your attention on. With regard to some of the other attributes that are not well-known mandatory, multi-exit discriminator is one that tends to get used quite a bit. Local preference is another attribute that tends to get used quite a bit. The remaining ones, I would say, are probably well beyond the scope of what we're doing in this class. But all right. So what are the prerequisites for BGP peers to be able to communicate to each other? We have to have a route to the next hop. So we establish peering by identifying the peer's next hop address that we're trying to communicate with. The other things here, I don't think we really need to go through. I'm kind of scanning through these. The last thing I wanted to talk about actually is the path selection process. All right, and I'm pretty much not. I'm not going to go through all of this because it's beyond what we need to know. But I would like to at least get to 7 or 8, right? Because most of the time when you're making policy decisions, you're usually not going much beyond 4 or 5 to make that policy decision. As you start to get down the tree, it becomes less and less likely that you need to continue further down because you've already made a policy decision prior to that. So we don't go through every single one of these every time. We make decisions incrementally on each one of these. If weight is an attribute that I'm using, and I have a prefix that's learned from 2 different sources, if you will, then I'm using weight as an attribute, then that's what I'm going to use to make my policy decision. And I'm not going to go beyond that. I'm just simply going to use weight and say, okay, highest weight is going to be used. All right. Is this a Cisco proprietary attribute? So it's not well known, and it is discretionary. It's used to influence the inbound policy, not the outbound policy. It's assigned locally by the router, and it's not propagated to any peers, and so on. I'm just trying to think if I want to take the time now to get into the details here, because in order to understand these attributes, quite honestly, you need to see them visually in a diagram. You need to say, okay, here's a diagram, here's a prefix, this is how I can reach this prefix. I'm using weight. How does that influence my decision? Reading about it is a little bit more difficult. So I'm just going to kind of give you the basic takeaways here. Weight is the first decision in the tree, because that's what you're going to see on the test, right? What is the order of preference of making a policy decision, right? In fact, you guys have probably seen that in some of your review questions. So weight is the first thing. It affects inbound routing. It can be a value from 0 to 65,535, and the higher the number, the more preferred. The default weight is 32,768 for paths that I originate, which means the next hop is quad 0 because I'm the next hop. I'm the one that's originating the prefix. If I'm not originating the prefix, then the weight is going to be 0. And you see this, by the way, in the show IP BGP command. When you run show IP BGP, you'll see weights tied to a particular prefix. Just remember, weight, the higher, the more preferred. All right? And then these are commands on how we can adjust that weight. I can actually apply a weight value to a neighbor. So I can say for all routes that I'm learning from this neighbor, apply a weight, or I can use a route map to set the weight for individual prefixes, and so on. After weight, the next decision is local preference. Local preference, if you remember, is a well-known mandatory attribute, right? Where's my local preference? Well-known discretionary attribute. So everybody knows what local preference is. Whether I choose to route by this or not is up to me. It's also an inbound policy, meaning that it affects inbound traffic. It's propagated throughout the AS. The default preference is weight. The default preference is weight. The default preference is 100. The higher, the better. And again, I can do this by setting kind of globally the value. It is not advertised to external peers, only internal peers. And it is carried through confederations, which we don't need to talk about. Okay? All this stuff, by the way, I talk about in detail in my CCIE class. So, prefer the path that's locally originated. So that locally originated is not really defined as a as a separate attribute. What's related to that is the origin code, which is a well-known mandatory attribute. And but origin is kind of sits down further on the list here, where we have origin type. So it wasn't learned via internal or external. So it's similar to that, but let me just kind of go through what it says here. I prefer the path that is locally originated using a network statement or an aggregate command. So aggregate would be like a BGP summary. That's how we do summaries in BGP. We use an aggregate command, or we use network statements to originate a prefix into BGP. So maybe it's a connected route on my router, and I'm inserting that route into BGP by using a network statement. That's what they mean by locally originated. So local paths that are sourced by implementing the network statement, or paths that were sourced into BGP by doing redistribution, or paths that are sourced into BGP by doing aggregate address, which is summarization, and so on. Locally originated routes, like we said before, have a weight of 32,768. Prefer the shortest Aas path, well-known mandatory attribute, and probably, quite honestly, 9 times out of 10, this is the attribute that's going to be the policy decider. I see it quite often when we manipulate path selection, how we reach particular prefixes by Aas path. Very, very simple decision tree. The shorter the Aas path, the more preferred the path. All right. And we can manipulate that using route maps if we want to do Aas Path Prepending. So we're adding hops, kind of virtual hops to the Aas path to make it longer, and so on. Step number 5, prefer the lowest origin type. If I learn about a prefix through an IGP process, I'm going to prefer this over EGP. That makes sense, right? If I know about a route through OSPF, I'm going to prefer the route through OSPF over IGP, over EGP, right? EGP is preferred over incomplete. Now, incomplete could be in there for multiple reasons. Typically, incomplete just means that it's a redistributed route, but we'll maybe get into that a little bit later on. Multi-exit discriminator, purely an outbound policy, and it's optional non-transitive. It is a suggestion to your peer on how they should enter your autonomous system. Now keep in mind, if you only have one link between autonomous systems, most of these policy decisions aren't going to matter. Aas Path is pretty much the only thing that is going to influence how you choose to route. But a lot of times autonomous systems have multiple ingress and egress points. That's when all these other attributes come into play. How do I decide to leave the autonomous system based on weight or local preference? Or how do I influence somebody to come into my autonomous system because I have multiple paths coming in from a peer AS? I can say use this path over this path based on a multi-exit discriminator. Multi-exit discriminator is also called a metric. Even though it's not technically a metric, when you do a show IP BGP, you'll see it listed in the BGP output as a metric. Lower is better in this particular case. We prefer eBGP over iBGP because, and that makes sense, right? eBGP has an administrative distance of 20, iBGP has an administrative distance of 200, and not to mention we prefer IGP protocols anyway over iBGP as well. Prefer the path with the lowest IGP metric, and then if I have multiple paths, if I've gotten down to this point and I still have multiple paths to choose from, then I start to go through the tiebreakers, and I'm not going to get into the tiebreakers in this case. It's just too much information. Well, it's already been too much information, most likely. You guys have probably like, geez, I didn't know that we were going to get into this. But anyway, the extent of what you need to know for the test is clearly not as advanced as what we just went through. But you can see how complicated BGP is as a protocol. A lot of individual decisions that take place in this policy kind of path vector attribute policy decision process. But there's two things that we take away from that. Number one, the protocol is highly customizable, right? It's what we call very, very extensible, meaning we can make lots and lots of unique decisions on how we decide to leave an autonomous system or enter an autonomous system based on these policy decisions, okay? So the next section here in BGP Operations, maybe a little bit of a summary of what we already discussed, but we'll see as we kind of go through this. Similar to other IGP protocols, BGP maintains relevant neighbor and routing information. We have three data structures in BGP. We have a neighbor table, we have a topology table, we have a routing table. So we know the different messages, right? Open, confirm, notification, and keep alives, right? To maintain a BGP session. So those are the message types. And that's one of the three major things that we learn about when we talk about protocols. The second is the data structures. We just talked also about the algorithm, if you will, even though we don't have a specific name for it. We talked about kind of the process, the decision tree that we use to make policy decisions. But the data structures are interesting because we have similar data structures that we have with all the other routing protocols. We have a neighbor table, which allows me to identify peering information. Show IP BGP neighbor is one way of seeing the details of your neighbor relationships, just like we saw with show IP OSPF neighbor and show IP EIGRP neighbor. Or we have show IP BGP summary. Show IP BGP summary also gives us neighbor information. Okay, but you can see here as an example, we have a neighbor of 192.168.1.11. The remote AS is 100. The BGP router ID is 10.0.1.1. And by the way, the router ID in BGP is selected exactly the same way it is in OSPF and EIGRP. The state is established, right? That is one of the multiple states that we would see, but this is the primary state that we'd want to see. There's no transitionary states that we should stay in. We can also see that the keep alive interval is 60 seconds. The dead timer is 180 seconds. That's pretty typical. We have two peers here, AS200, AS100. Also notice it says external link, which indicates that these are eBGP peers. And this is a very, very truncated output, by the way. I mean, the show IP BGP neighbor command shows you tons of information about those peers. Pages and pages of information about those peers. So that's a very, very truncated output. Show IP BGP, which is the blue box there. That is my topology database, or what we refer to as the BGP rib. All right. It lists all of the possible prefix destinations and all of the ways that we've learned about those prefixes. Okay, now keep in mind, like EIGRP, a neighbor is only going to advertise what they're using. So the only reason you would have multiple entries for a particular prefix is if you have multiple neighbors telling you about that prefix. You would never have one single BGP peer giving you lots and lots of different information about an individual prefix. If I'm router A and I've learned about a destination through 5 different routers, I make a decision on how to route to that prefix. That is the only thing that I advertise to my peers, is the decision that I made. That is, again, very much like a distance vector concept, isn't it? EIGRP operates the same way. EIGRP only advertises what it uses. It doesn't advertise everything it learns. OSPF is the opposite of that, right? OSPF advertises everything it knows. So you can see here, and we'll certainly dive into this a little bit in more detail, but because again, this blue box is kind of truncated, there should be a key at the top that describes what all these things mean. But an asterisk means that that's the route that's being used. A greater than symbol means it's a valid path. The network is the prefix, is the destination. Next hop, remember that's a well-known mandatory attribute. A quad 0 next hop means that I originated this route, and a next hop of not quad 0 means that I learned this route from somebody else. And see the weight column here? Remember we talked about weight? 32768 is a well-known mandatory attribute. And it means that that's the default weight for routes that I originate. 0 is the default weight for routes that originated from somebody else. Metric, multi-exit discriminator. Local preference, Aas Path, origin code. So these are all those well-known mandatory attributes that are applied to these prefixes. Actually, metric is not well-known mandatory, but in Cisco, they do include the metric in the table by default, right? So these are just 4 of the attributes that we see in the BGP table. One of the things that you'll see on the test is that you're going to have to look at a diagram of a BGP database, a show IP BGP output, and you're going to have to decide what prefix is going to be used based on that decision tree that we talked about. Aas Path, the origin code, a local preference weight, etc. The routing table itself is just a global rib, right? It's not specific to BGP. It's just the global routing table. Notice in this particular case, we have 2 BGP routes, 10.0.1.0 and 10.0.2.0. I know that these are eBGP routes, not iBGP routes, because of the administrative distance. That we also know that because we said that those are external links at the top. And we also know, well, next hop doesn't necessarily guarantee, a next hop of not quad 0 does not necessarily guarantee that it's eBGP, because you can have next hops of iBGP as well. But because the administrative distance is 20, we know that these are eBGP routes, and the metric is 0, right? So this metric here is not the same as this metric here. This metric here is just the metric, which we don't have. We don't have a traditional metric in BGP, so that number is always going to be 0. All right? All right. So again, the message types, which we had in the text document, this is good that we see this here. Open to establish the session, keep alive to maintain the session, update to process routing information, and notification if there's an error. All right? After a TCP connection is established, the first message that is sent by each side is an open message. If the open message is acceptable, okay, now why wouldn't it be acceptable? It might not be acceptable because you maybe mistyped the neighbor statement, or the source address of the open message doesn't match the address in the neighbor statement, because maybe we were trying to establish a peering relationship between our loopbacks. We did not use the update source command, and the IP address of the open message happens to be the egress interface on the router or something like that. So there's lots of reasons why I might get a BGP open message, but I might not transition through the process of establishing the session. After the receiving side confirms the open message and establishes the BGP connection, which is the TCP three-way handshake, the peers can exchange updates, they can start sending keep-alives, and if there's a problem with the exchange of information or the peering relationship, we can send notification messages. Open message includes the version number, highest common version of both routers, support is used. We don't really need to get into the differences between BGP versions, but BGP version 4 is typical. The ASN, it's the autonomous system number that actually defines the rules of engagement, right? Matching AS, iBGP engagement. Different AS, eBGP engagement. And actually, there are some differences between an iBGP pairing relationship and an eBGP pairing relationship. Hold time, 60 seconds, we talked about that. The BGP router ID, same as OSPF, manually set, highest loopback, highest physical interface, and then some optional parameters as well. Again, BGP is a very extensible protocol. There's a lot of customization you can do with BGP. BGP speakers send keep alive messages to ensure that the connection between the BGP peers state is maintained. Keep alive messages are exchanged between the peers on a periodic basis, enough to keep the hold timer from expiring. We already saw what that default value is, 60 and 180, right? If the negotiated hold time interval is 0, we do not send keep alives. That actually is pretty common. A lot of service providers will rely on other mechanisms to identify whether or not a BGP peer is still active. They'll use something like bidirectional forwarding detection. They'll use link status or something else to identify if a peer is active, because we're trying to reduce the amount of communication. You have to understand that as a service provider, you might have hundreds of peering relationships or thousands of peering relationships. So having to send keep alives for each of them is not very practical. So you can actually turn off the keep alive mechanism and just rely on other ways to identify whether or not a peer is still active. BGP peers initially exchange their full routing tables using an update. Incremental updates then get sent after topology changes occur. So that's kind of like eIGRP, you know, the advanced distance vector concept. Actually, it's very much like eIGRP. The BGP update message has information that is related to a path only. Multiple paths require multiple update messages. The attributes in the update messages refer to that path. Those are the attributes that we were referring to: weight, local preference, MED, Aas Path, etc. That's how we identify reachability to those particular destinations. Updates can occur if we're withdrawing routes, if we modify the path attributes, or if the network layer reachability information needs to be updated. Okay? Notifications are sent only if there's errors, and there's an error code indicated in the notification message that can identify what specific error has occurred. Which BGP data structure stores the updates that are received from a neighbor? Okay, that would be the BGP table. BGP table is the topology table. All right, the neighbor table is, of course, related to the neighbors. The routing table is the global routing information base that we put BGP routes in after we've gone through our policy filters, right? Identifying which routes prefixes we're going to use. And there's really no such thing as a BGP update table. All right, neighbor relationships. We've kind of already talked about this, very, very brief section here, but there's really only two types of neighbors or peers that you will have: an Ibgp peer and an eBGP peer. The configuration of these peers is actually the same. You define neighbors statically, just like you do, in both cases you define neighbors statically. And whether the neighbor AS matches your AS or not really is what determines whether or not this is going to be an Ibgp or an eBGP relationship. There are a couple of kind of differences between these adjacencies. For example, eBGP pairing relationships by default have to be link local, meaning that we cannot peer over multiple hops. You can override that behavior by using an eBGP multi-hop command. Ibgp pairing relationships are virtual. They can go over multiple hops by default. You know, how the next hop attribute is modified, how information is propagated, of course, the administrative distance of routes that are propagated. Ibgp peers typically have to have either a route reflector or you have to have you know, a full mesh and so on. So there are some kind of unique characteristics to each of these, right? They're not quite the same. But overall, the configuration is very similar. Okay, an eBGP pairing relationship literally is any two routers or BGP speakers that have different ASs that are peering with each other. So, for example, on the left diagram, ASX and ASY would be eBGP peers. ASA talking to ASX would be eBGP, but ASX on the right everybody talking to themselves would be considered an iBGP pairing relationship. And a lot of the rules change when you go to iBGP because generally speaking, we don't like to use iBGP pairing relationships to be able to establish routing reachability information. We usually will rely on our IGP protocols like OSPF and EIGRP for network layer reachability information within an autonomous system. So iBGP pairing is typically going to be seen when you're implementing some sort of transit AS. So you're taking external routes from an eBGP peer, you're passing them through your autonomous system, and then you're sending those routes to another eBGP peer on another in another in another autonomous system. That's typically when you're going to see some sort of iBGP kind of relationship. Does that make sense? So it's not very common to see iBGP used consistently in a standard design. With internet connectivity, eBGP is used to advertise internal customer routes to the internet through multiple ISPs. eBGP is also commonly run between the customer edge and provider edge routers. The requirements to establish an eBGP pairing relationship include different AS number, right? That's the whole point. TCP sessions must be established before starting the exchange of routing information. So, and we do that by the way of by establishing or identifying the neighbors using a neighbor command, which you guys will see in the lab exercise shortly, right? We use a neighbor command to establish adjacencies. So the very first thing you should always do before you would try to establish a neighbor adjacency with an eBGP peer or even an iBGP peer for that matter is to make sure you have reachability. Ping that address. Make sure you can get to that address before you try to establish an adjacency. Otherwise, you're just going to be wasting your time, right? Reachability by default, eBGP peers must be directly connected because the time to live for the TCP messages is 1, which means that it's non-routable. But you can override that behavior. You can actually create peering relationships between external routers over multiple hops. You just have to change the configuration to do that. By default, which two of the following are conditions that must be satisfied for routers to be eBGP neighbors? They must be directly connected. We just talked about that. They must be in different autonomous systems. You don't have to be running an IGP between them to establish an adjacency. If they're directly connected, obviously you're not going to run any protocol to establish an adjacency between them because they share a common subnet. If they're not directly connected, you could use a static route, you could use default routing, you could use some other routing protocol as well, but usually it's either going to be a static route or a default route. All right. This we also kind of talked about a little bit. I think we went into it in a lot more detail than in our last section than you're going to see here, so I'll kind of summarize this. But the BGP Path Selection process is based on policy, not bandwidth or metrics, not traditional metrics. All right, and I think we covered that in quite a bit of detail. In a multi-home deployment, BGP routers have several peers and receive routing updates from each neighbor. And we talked about that. And on the internet, that's very, very common, right? Your AT&T is not going to just peer with one other provider. They're going to peer with hundreds of other routers and potentially multiple, well, definitely multiple providers. They have actually peering policies that they publish. They have peering policies that they publish that define how you're supposed to establish an adjacency with them. You know, what kind of rules are you going to follow and so on. So in this particular case, we have to make decisions on how we're going to route. And as I mentioned in our previous discussion, routing decisions are based on policy. There are some policies that affect inbound routing, and there are some policies that affect outbound routing from the autonomous system and so on. The BGP best path algorithm is evaluated against any other routing protocol that can also reach that network. The route from the source with the lowest administrative distance is installed in the routing table. So again, just because I can reach a prefix with BGP does not mean I'm going to use BGP. You know, our standard routing process still applies. If I learn about a route through Ibgp and I learn about a route through OSPF, the same prefix, I'm going to use the OSPF route because it has a lower administrative distance value than Ibgp. All right. What is this process? After BGP receives updates about different destinations, it chooses the best path based on path vector attributes. Highest weight, which is local to the router. So that would be a situation like this. Let me give you a visual real quick, where I might have an autonomous system. So here's my autonomous system, and here's a router that I can use to leave that autonomous system, right? There's my router there. And this router has external connections either to different autonomous systems or the same autonomous system. I'll just put a couple of clouds in here. And it has two ways that it can, you know, get to some destination prefix. So maybe there's a prefix over here of 10.10.10.0/24, right? And this router needs to decide, am I going to go this way or am I going to go this way? All right. Now, Aas Path could be used. In fact, Aas Path pretty much would be used if we're not modifying the weight value. But weight is a way for this individual router. It's local to the router. Weight is a way for this individual router to decide to go that way or that way. So what's happening is this router here is advertising that prefix, and this router here is advertising that prefix. When we say this is an inbound policy, what we're saying is okay, I can use a route map to apply a weight of, say, 100 here. The weight here is going to be 0. Remember, the default weight for routes that I don't originate is 0. So I can apply a weight of 100 for that prefix, which influences how this router decides to route to that destination. We call it an inbound policy as opposed to an outbound policy because we're applying the policy to the prefix that's being learned inbound. It's not because we're routing inbound, it's because we're applying the policy to the prefix that is inbound, that we're learning in from another autonomous system. You see how visually, if you see it visually, it makes more sense than if you just read about it, right? None of the other routers in here care about weight, even if they're Ibgp peers, because it's a local decision. This router makes its own decision on how to route to this prefix based on a weight that's applied. If the weight is default and it's 0 and 0, then we go to the next policy decision. Make sense? Okay. So that's what the weight attribute is. The local preference, this is another one that is useful to see visually. So local preference is completely different than weight. Weight is by the way, a Cisco proprietary attribute. Local preference is a well-known attribute, so it's not Cisco proprietary. So local preference is an attribute, is also an inbound attribute. So it's applied to prefixes that I learned from my peers. So my OCD is kicking in here, but so I might have a connection to this AS, I might have a connection to this AS, and again, we're learning about 10.10.10.0/24. 10.10.10.0/24, and I need to decide how I'm going to leave the AS, right? So these are both routers, and by the way, those routers are advertising this prefix inside, and there could be some other iBGP routers internally. So we set the local preference, we apply the local preference to the inbound route that we learned here on this router. We apply the local preference to the inbound router that we learned on this router. That local preference is then propagated to the other routers in the autonomous system, and then based on that local preference, they will choose to go this way or they will choose to go this way to leave the autonomous system. So a lot of people will look at this and they'll say, oh, that's an outbound policy. It affects outbound routing, but we apply the policy inbound. We apply the policy to prefixes that we're learning inbound, right? So they didn't really get into this, but let me actually go over back to this document, and we'll take a look at this again now that we've kind of seen these visually. So wait is an inbound policy. You now understand what that means. It's assigned locally by the router. You understand what that means. It's not propagated to any other peers. You understand what that means. 0 for prefixes that I learned from somebody else. 32.768 for prefixes that I learned by myself. I mean, if it's a prefix that I'm originating, then weight doesn't really matter, does it? Because we're not choosing how to route to that prefix. It's one that I'm originating. Higher is better, and so on. Local preference, also an inbound policy. And it propagates through the autonomous system. So it doesn't move from one autonomous system to the other. The default preference is 100, and a higher number is better. All right. So that's another attribute that once you see it visually, it kind of makes more sense. And that document that I told you guys about at the beginning of our discussion, the BGP Best Path Selection process on Cisco.com, has visual representations of all of these attributes. And it also gives you configuration examples and how you can manipulate those values. It's a really, really good document to learn about these attributes. Okay. Origin, we don't really, originated by the router, we don't really need to visualize, right? Because I prefer routes. If I have a route to 10.10.10.0/24, and it's in my BGP table with a next hop of quad 0, but it's also in my BGP table with a next hop of somebody else, of course I'm going to use the quad 0 one, because that's me, right? I'm not going to route to somebody else to eventually get back to me. So I'm going to prefer my own routes over the same route I might learn from somebody else. Aas Path is pretty self-explanatory as well, meaning that the shortest Aas Path, the shortest number of autonomous systems that I have to go through, and then origin code. Interior routes are going to be preferred over exterior routes, which are going to be preferred over incomplete. And then multi-exit discriminator. That's another one that you kind of need to see visually. And MED, if you'll notice here, is defined as an outbound policy. Aas Path can be inbound or outbound, but multi-exit discriminator is an outbound policy. So this diagram that I already have is perfect because I'm advertising prefixes to the peer. So in this case, I've got prefixes that I'm sending out. Maybe it's a 1.0.0.0/8 prefix, and I'm advertising that prefix out to this peer. And my diagram's not quite right here. Let me make one change. Get rid of that line there. And let's put the line right here. Okay. And what I can do in this case, and this could be the same router. We'll just put a same router here, make it simple. These are my routers. I'm not going to do the other one because there we go. Fill in my whole diagram there. All right. So MED is a recommendation by me on how you should route to my prefixes. So I'm going to send a med value to you. I'm going to send a med value to you. And then you can choose to route based on that value. I can only suggest something. You can ultimately decide whether or not you want to take that suggestion or if you want to override it with your own policy. Like I said, in most cases, providers will kind of work with each other and they'll kind of accept whatever another provider suggests. But this multi-exit discriminator is a way for me to influence how the peer routes to me. So, you know, this guy could be using local preference or wait to decide how to route. It could be using Aas Path. I mean, it could be, we can be doing Aas Path Prepending to add Aas hops to this link or this link to make it worse or better. And that's an inbound or outbound thing. I can choose to do Aas Path Prepending inbound for prefixes I'm learning from a peer, or I could choose to do Aas Path Prepending for prefixes that I'm advertising out to a peer. But multi-exit discriminator is to say, hey, I prefer you to come this way based on the med value that I'm sending you. You can choose to ignore it. You can choose to follow that recommendation. It's up to you. It's an optional attribute, so it's not something that you're required to follow. Hopefully that makes it a little bit easier to understand. And that's, again, why that document from Cisco.com is so important, because it really does go into detail on each of these attributes and gives you some visual references to look at, because that's what you need to really understand how these attributes are applied. But I covered most of the important ones. All right. Routing policy is based on factors called attributes. I prefer an eBGP path over an iBGP path. I prefer an iBGP route. We're kind of getting down to the tiebreakers, you know, the stuff that doesn't really come up that much. I prefer for an iBGP route, I prefer the path through the closest IGP neighbor. So iBGP pairing relationships are virtual, which means that most likely there's multiple hops between those BGP speakers, and those multiple hops are reachable through some sort of IGP protocol like OSPF or EIGRP. So if I'm learning about the same prefix from multiple iBGP speakers, and I haven't made a decision based on any of the other attributes, and I get down to this point, I'm basically going to say, okay, which is the closest iBGP speaker based on the metric of the IGP protocol, right? And now we're getting into some of the really, really interesting tiebreakers. Oldest eBGP path, the longest uptime, the path with the lowest router ID, the path with the lowest neighbor IP address. I mean, you're very rarely getting down to these choices when it comes to BGP routing. You've already made a decision well before this, okay? It should be getting a little clearer. You know, as we kind of keep hitting these points and going over them, the picture should be getting a little bit clearer. When faced with multiple routes to the same destination, BGP chooses the best route for routing traffic towards the destination by following a route selection process. For example, suppose there are 7 paths to reach 10.0.0.0. No paths have AS loops, so that's a really important concept, because I would ignore any path that has my autonomous system in that path, because that would be a loop in the topology. All the paths have valid next hop addresses, so all 7 paths proceed to step 1. We examine the weight of the path. All 7 paths have a weight of 0, which means they're learned from somebody else. So all paths proceed to step 2. Ultimately, what happens is we keep going through this until we've selected one path. Remember I told you guys we were talking about ECMP for OSPF, and I said BGP doesn't do load balancing. And it doesn't. It doesn't do load balancing because it goes through the decision tree until it's chosen one path per prefix. So there's always going to be a tiebreaker. Always going to be a tiebreaker. So we don't really have traditional load balancing with BGP. All right. All 7 paths have a weight of 0, so we go to step 2. 4 of the paths have a local preference of 200. The other have 3 have a local preference of 100, 100, and 150. So the 4 paths with a local preference of 200 now have eliminated those other 3. So now we're down from 7 to 4. We continue the process. The other 3 will still be in the BGP forwarding table, but currently disqualified as the best path, which means that if I do a show IP BGP, I'll see them in the database, but they won't have an asterisk next to them. They'll just have a greater than symbol next to them, indicating that they are valid, but they're not being used. So BGP continues to evaluate this until only a single path remains. That's the one that gets the asterisk in the BGP table. That's the one that ultimately goes into the global RIB. All right. I like the bullet point here. The route selection process that is summarized here does not cover all cases, but is sufficient enough for this class. All right. Which 3 of the following attributes are considered by BGP to select the best path? Weight, local preference, Aas Path. No such thing as vector. Aas number Aas numbers exist, but it doesn't play a role in deciding how we're going to route. And administrative distance, of course, would only be if we were learning about the path through 2 different routing information sources. So we're going to hit this up again. I mean, it doesn't hurt to look at it multiple times, right? We've already kind of discussed everything in here, in that text document that I created, but this document kind of breaks down the attributes in a little bit more detail. Well-known, mandatory, discretionary, right? Mandatory means that you have to use those attributes. There's only 3 well-known mandatory attributes: origin, Aas Path, and next hop. By the way, all those show up in the show IP BGP output. A well-known discretionary attribute, as I mentioned, is everybody understands it, but whether you decide to use it or not is up to you. Optional means you may or may not understand it. It may not be part of your BGP implementation. Transitive means that it moves through from one autonomous system to another. Community attributes and aggregator attributes move from one autonomous system to another, not just to the peer AS, but beyond the peer AS. Whereas non-transitive only move to the peer AS and they don't move beyond the peer AS. Hopefully now, I mean, if you had seen this prior to our discussion, this would probably not make a whole lot of sense, but hopefully it makes sense now. Okay? But we'll go through it again just to make sure. All right. Well-known attributes are attributes that all BGP speakers are required to understand in their path determination process. There are 2 categories, well-known mandatory and well-known discretionary. Every update must include the mandatory attributes. Updates don't necessarily have to include the discretionary attributes. Origin. When a router first originates a route in BGP, it sets the origin attribute. If information, I'm reading this because we actually didn't get into this in a lot of detail in our previous discussion, so this is good. If information about an IP subnet is injected using the network statement, meaning that we originated a route in BGP, maybe it's a connected interface, maybe it's a loopback or a physical Ethernet interface or whatever, and we put in a network statement so that that network would be included in the BGP process. That's what they mean by origin. Or via aggregation, so we're using a summary address command or an aggregate address command, or the origin the origin attribute in that case would be set to I for IGP. Okay, so that means, it doesn't mean like OSPF or EIGRP. It means that I'm the one that's generating the prefix. If information about an IP subnet is injected using redistribution, the origin attribute is set to a question mark. for unknown or incomplete information. Basically the same meaning. If the origin code is an E, that's used when the internet was migrating from EGP to BGP. So the E you should never really see. Now going back to our list here, origin type is number 5 in the list, right? That's number 5. So routes that are generated from the network statement or summaries are preferred over routes that are redistributed. Ultimately, that's what it means. E doesn't really matter in this case. All right. So that's what they're mentioning about the origin code. Aas Path, we know about that. That's pretty straightforward. The number of Aas hops I have to go through to reach a destination. Next hop is an attribute that absolutely must be set. There's 2 types of next hops that you'll see. You'll either see a quad 0 next hop, which means that you're the one originating the prefix, or you'll see a non-quad 0 next hop, which means somebody else is originating that prefix. And that next hop needs to be reachable in order for the prefix to be valid. All right? So the next hop attribute is very, very important. How that next hop attribute is set and maintained depends on whether it's an eBGP relationship or iBGP. Sometimes the next hop gets overridden with your information if you're repropagating a prefix onto the destination. Sometimes the next hop attribute is maintained, which can actually cause some issues. You guys have probably seen, if you've done any BGP, next hop self being applied to a neighbor relationship. It just has to do with how we write that next hop information and represent it to the peer. All right. A well-known discretionary we already talked about. Local preference we already talked about. Atomic aggregate. The atomic aggregate attribute is attached to a route that is created as a result of summarization, aggregation of BGP routes. It just sounds cool, atomic aggregate. This attribute signals that the information that was presented in the original routing updates may have been lost when the updates were summarized into a single entry. Kind of beyond the scope of this class, but it makes sense, right? When you summarize routes, how do you take attributes from various prefixes and include them in an individual prefix? What if the routes that I'm summarizing have different local preferences or different weights or different Aas paths? When I summarize the routes, what happens to those attributes when I aggregate them together? So an atomic aggregate allows me to kind of represent policies or at least path attributes for those summaries in a specific format, right? And it might include aggregating some of those attributes. Certainly we can't aggregate weight or local preference, but we can aggregate things like Aas Path. And so that's why they call it an atomic aggregate. All right. Optional attributes, again, you don't necessarily need to understand them. They don't need to be implemented in your particular version of BGP. Remember, BGP has so it's a highly extensible protocol, which means it has the ability, we have the ability of customizing the protocol with different attributes that may not be supported by everybody. I would say optional transitive attributes are beyond the scope of this class. Certainly community is beyond the scope of this class. Aggregator, very similar to the atomic aggregate when we do summarization. The med is probably one of the most common optional attributes. It is, in fact, the most common optional attribute. So, and we did discuss that. It's a way for us to influence how traffic influences inbound traffic decisions by applying an outbound policy, right? We're applying outbound values to prefixes that we're advertising to our peers. All right. And then we get our pretty little diagram. So we'll go through this again because it doesn't hurt to see it more than once. Weight, local to the router, router 1. We we've learned about the 209.165.201.0 prefix from AS 65010 and from AS 65030. As those prefixes were advertised in from the peer, I applied a weight to that prefix. This basically influences how router 1 decides to route to that destination. Aas path would be a tie, wouldn't it? Because this Aas path is the same length as this Aas path. So in this case, if I wasn't using weight and I wasn't using local preference, I would have to kind of get down to some of those tiebreakers to make my routing decision. All right. Let's see. Weight is configured locally. Weight can have a value from 0 to 65,535. Paths that the router originates have a default of 32,768. Anything that's not originated by the router is 0. And in this particular case, we applied a higher weight from router 2. How do we do that, by the way? Well, we create a route map. And we do a match condition on maybe a prefix list. And the prefix list references the prefix. And then we do a set condition. We actually literally say set weight. And that allows us to set the weight of that particular prefix. And then we apply that route map to that neighbor relationship. So route maps give us all kinds of flexibility on applying all kinds of different attributes to different prefixes that I might get from a particular peer. Local preference. As I mentioned, this is a way for us to kind of influence how other routers inside the autonomous system decide to leave the AS. So we have two routers that are connected to an AS. Router 1 has a local preference of 150. Router 2 has a local preference of 200. So all the routers inside of 65040 will choose to go to router 2 for whatever particular prefix we've set, right? Depends on the prefix, but in this case it's 209.165.201.0. Okay? Similar to weight, except it's not local to the router. It's propagated throughout the AS. All right? And we would we would manipulate this value the same way that we would manipulate any other BGP attribute. We'd create a route map, match the prefix using a prefix list in a route map. I'd set up a prefix list to match that prefix. I'd go to my route map and say, route map, local preference, permit 10, match IP address, prefix list, PFX1 or whatever, set local preference. And then it would set the local preference for that route. And then once it's set, by the way, because it is a well-known attribute, it's going to be propagated to the rest of the peers. Aas Path, probably one of the simplest attributes to understand. If it's 3 ASs to get to the prefix through one way, and it's 2 ASs to get to the prefix the other way, I'm going to choose the path with 2 ASs. So that's a pretty simple attribute to understand. Now we can manipulate this. I can do something called Aas Path Prepending, where I could say, in order to make a path appear to be longer, I could add my Aas path multiple times if I wanted to. So I could come into router 2 and say, to get to 209.165.201.0, it's going to be AS 65040, AS 65040, AS 65040, then AS 65030, then AS 65020. So I'm basically tricking the router into thinking that it's more hops than it really is. All right. So, and there's all kinds of, you can do filters and, prepending. You can push an outbound policy, or you can push an inbound policy with Aas Path. It's pretty straightforward. Multi-exit discriminator, like I said, is a way for me to influence how somebody routes to me, right? So this is my AS. This is my prefix that I'm advertising, and I'm attaching a med to that value. In the case of med, lowest wins, not highest. Why, I don't know, but they did highest on everything else and did lowest on this. But This is a suggestion to the peer, right, as to how I want you to come into my autonomous system. Like I said, this is not a value that you necessarily have to follow. You can choose to, and a lot of service providers will choose to do that. They'll choose to follow that. So MED is an attribute that is initially exchanged between eBGP peers. It's non-transitive, right? So once it gets to the next autonomous system, it stops there. It doesn't go beyond that autonomous system. And the default value of the metric is 0, and the lower the value is the more preferred path. All right. Which statement correctly describes the wait attribute? It is initially exchanged between autonomous systems. It is only exchanged via Ibgp. It is only exchanged via eBGP, or it is local to the router. It is local to the router. Which statement correctly describes local preference? It is initially exchanged between autonomous systems. It is only exchanged via Ibgp, check. It's not external, it's internal, and it's not local to the router. It's sent throughout the entire autonomous system. Again, only BGP speakers, right? It's not sent to OSPF or EIGRP because they don't understand this stuff. They don't use this stuff. All right. Which two statements correctly describe the MED attribute? The higher value is preferred. No, lower value is preferred in this case. For the wait and local preference, higher value is preferred. MED is initially exchanged between autonomous systems. Yes, that is true. The MED is local to an AS. Nope, it's sent from one AS to another, and it is not maintained across all ASs because it's non-transitive. So it only goes to the peering AS. Which three of the following attributes are required to be present for every route in every update? So these are our well-known mandatory attributes. Next hop, Aas Path. What else? Origin, right? Local preference is, go back to the list here. Origin is well-known mandatory. Aas Path is well-known mandatory. Next hop, well-known mandatory. Origin, not origin, community, optional transitive. What were the other ones we had? Aggregator. Aggregator, optional transitive. And local preference. Yeah, that was the one I was thinking of. Well-known discretionary. So it is well-known, but again, it doesn't have to be included in the update because it's a discretionary attribute. All right, everybody, welcome back. We are going to go ahead and go into our discovery for BGP, discovery number 11, configuring and verifying single-homed eBGP, exterior BGP. So throughout this discovery, we're going to configure external BGP between the service provider router and the two customers that we're servicing. We're going to configure the service provider SP1 to establish separate single-homed eBGP sessions with each of the customer routers, router 1 and router 2. In this particular exercise, all of the IP addresses are already completed. The devices have their configuration, the host names and IP addresses. The customer routers, R1 and R2, are also already pre-configured with BGP so that they can peer to the provider. So we're going to configure a single-homed eBGP session between the service provider and its two customers, and then we're going to verify that single-homed eBGP session by analyzing the neighbor relationships and by exchanging routes with that particular peer. All right, so the first task that we have in this particular exercise is to configure single-homed eBGP. All right, now the information that we need to have in order to do this or to complete this configuration is we need to have the autonomous system numbers, both the local router autonomous system number and the remote router autonomous system numbers. And we can see in this particular case, BGP autonomous system number 1 is the service provider side. AS100 and AS200 are the customer side. All right, we also need to know that all the peers that are involved in the BGP sessions and IP addressing that's used is going to be available, that we have neighbor reachability, because we can't establish the TCP session or the BGP session with the peer unless we've already confirmed that we have reachability with that particular address that we're trying to peer with. And then we also need to identify which networks we want to make sure are going to be advertised into BGP. So as I said before, BGP is already pre-configured on the customer side. Let's go ahead and take a look at the configuration on router 1 to start with. We'll go over to router 1 and we're just going to do a show run section BGP. And let's take a look at that configuration. So we can see we're running autonomous system number 100. That happens to be a public AS in this particular case, but we're not, not a big concern here because we're doing this in a lab environment. We can see that we have the neighbor defined 1.10, so we're doing physical peering. We're not peering to a loopback interface or some virtual IP. We're actually peering with the next hop. And the remote AS is identified as autonomous system number 1. Because my local autonomous system number is 100 and the remote AS is 1, this automatically determines that we are establishing an eBGP, or an exterior or external BGP session between the peers. We also have a network statement that says we're going to go ahead and advertise the 10.0.1.0 network. Now, the network statement in BGP plays a completely different role, right? It doesn't enable the protocol on the interface. The neighbor statement essentially is what enables the TCP session on the interface based on connected route information and the address that we're trying to peer with. What the network statement does in this case is it says this is a network that I want to inject into the BGP rib and then exchange that as part of the topology information or the NLRI or network layer reachability information. One of the key things, though, is that we need to make sure that we have a 10.0.1.0 route in the routing table and that the prefix length matches what we have in our network statement. If this mask did not match the mask of the prefix in the route in the routing table, then this network statement would not accomplish anything. We talked about that as part of our lecture discussion. Network statements need to match what is in the actual routing table in order for those networks to be advertised. All right, so next we'll go check the configuration of router 2, show run section BGP. We see a similar thing here. This is BGP 200. We're pairing with 2.10. And by the way, I would probably do something like this as well. Just make sure I can ping 2.10. I'm also going to do a show IP route 10.0.2.0/24. Oops, sorry. I could do this 255.255.255.0. Make sure that the route is in the table. And of course, that's going to correspond to the network statement that we have listed here. All right. Unlike our IGP protocols, BGP routers, even though they form an adjacency, do not automatically exchange routing information with each other. We have to explicitly identify which routes are going to be advertised by using the network statements, and those network statements have to correspond to a route in the routing table. It could be a connected route. It could be a route from another routing process. It doesn't really matter, but it has to be in the routing table. So our next step is to go ahead and enable BGP on the service provider router. I'm going to do a quick show IP interface brief just to make sure I have my IP addresses available. Config T, router BGP1. Now we can only run one BGP autonomous system in the router, unlike EIGRP and OSPF, where we can run multiple autonomous systems or multiple processes. With BGP, we're only allowed to run one BGP process. In this case, we're using AS1. Now, the AS number itself can either be a 16-bit integer from 1 to 65,535, or it can be a 32-bit AS number, which is basically just two 16-bit AS numbers separated by a dot. That gives us kind of more autonomous system numbers to work with in the future. So now we're going to define our neighbors. We're going to go ahead and say neighbor 192.168.1.11. The remote AS in this particular case is going to be 100 for that peer. And then I'm going to do 2.11, and the remote AS is going to be 200 for that peer. Now what's happening in this particular case, and let me go ahead and pull this up, is that we are establishing a TCP session between these routers. BGP runs over TCP. It is actually an application layer protocol, and it uses TCP to establish a peering relationship. We can identify actually who's the client and who's the server by investigating the TCP messages that are going back and forth. We talked about some of the different TCP messages that are sent, but we can see here in this particular case, the source IP is 1.11 and the destination is 1.10. The source port is 28997. The destination port is TCP port 179. That tells me that in this particular case, 1.10 is the server and 1.11 is the client. And that's kind of arbitrary. It really depends on who sends the open message first and then who responds to that open message as part of the process. But you can see from this BGP header that we have, actually let's go to our TCP section here. We don't actually see the BGP information, but we can see the source port, the destination port, and so on. All right, and of course the rest of the TCP information. We have our keep alive message as well. We don't send hello packets with BGP. We actually send keep alives, and those keep alives are sent every 60 seconds. We'll take a look at that as part of our investigation as well when we're doing our discovery here. So we've already seen several of the different types of messages. Let me go ahead and do a reset real quick. Do clear IP BGP star. So we can actually see all of the different BGP message types. And we can see in this particular case, we should see an open message. We should see keep alives, updates, and we don't see any notifications. Notifications is another BGP message type that we could potentially see. Here's the session closing, if you will, the fin, ACK, and fin, ACK. And then here is the three-way handshake to reestablish the session. So in this case, 1.10 is acting as the server. 1.10 is acting as the client. 1.11 is acting as the server in this case. So this is actually our three-way handshake to establish the BGP session. This is the open message saying, okay, now we're going to go ahead and start the BGP application. We're going to send an update to send information. This is an acknowledgement to the update. Here's another update. This is the acknowledgement. So we can see this is the update from 1.11 to 1.10. This is the update from 1.10 to 1.11, and so on. So it's a really simple protocol from a communication perspective. Once we've done the updates, pretty much from that point forward, we're just sending our keep alives every 60 seconds or so to maintain that session. All right, now who becomes the server and who becomes the client? Again, as I mentioned, really depends on who actually sends that TCP send request first. All right, now by default, and especially with eBGP, the IP address that's used in the BGP neighbor command has to be reachable without using an IGP protocol. So it either has to be a static route or it has to be a directly connected route. And in most cases with eBGP, it would be a directly connected route. If we were going beyond the next hop, we would have to configure a multi-hop configuration, because if you look at the message types, if we go back to our capture here, and we look at the update, for example, you're going to notice in the actual IP packet header that the time to live is 1. That's because external BGP messages are non-routable. They're only intended to go to a directly connected peer. Now I can change that behavior by using eBGP multi-hop, but by default the time to live for those eBGP messages, whether it's a keep alive, whether it's an update, let's take a look at our keep alive here. We see a time to live of 1. Our original BGP open, also a time to live of 1. And that's just by design. eBGP uses a default TTL of 1 when it's sending its information. We can change that behavior, but it's not generally recommended unless you're peering over parallel links or you have redundant connections between two different eBGP peers. All right, so we're going to see messages indicating that the peering relationship has taken place. The next step in our configuration is to specify the networks that we're going to advertise. Just like any other protocol, to specify the network that needs to be advertised, we use a network statement to be able to include that particular network. But the difference that we have here, let's say, for example, in this particular case, I want to advertise this 10.0.3.0 subnet. Now, if I go into my BGP process and I simply say network 10.0.0.0, thinking I'm just simply putting in a classful network statement, so it's going to include any networks. If I go to router 1 and I do show IP route BGP, you'll see that I don't have the 10.0.3.0 route, right? And the reason I don't have that 10.0.3.0 route is because there was no 10.0.0.0 route in the routing table. All right, so I actually have to put in a network statement that matches the prefix in the routing table. And then once I've done that, then that route is going to be advertised to the neighbor. All right, now there's a couple ways we could do that. We could maybe create a static route to a null zero interface, almost like a summary. We can do an aggregate that we can push into BGP as well. It just depends, right, on what our overall objective is as far as injecting the routes in the routing table. All right, so we want to make sure that we have an exact match. If the route is not in the routing table, it will not be advertised into BGP regardless. All right, so the meaning of the network statement in BGP is very different from the meaning of that particular command in other routing protocols. In other routing protocols, the network command indicates basically the interfaces that we're going to be running the protocol. In BGP, it just means that the routes that should be injected into the BGP rib on the local router, which then would in turn get exchanged through the BGP process and so on. So let's go ahead and go through a couple of different tasks here to verify our BGP process. Let's go into SP1. And there's a couple ways that we can do this. We can do a show IP BGP summary, right? And we can see here that we're running, this is our router ID. The router ID is selected the same way as it is in our IGP protocols. It can be statically configured, or it's going to be the highest active loopback or the highest active physical interface IP. We can also see how much memory is being utilized by BGP in this particular case. These are the defined neighbors, the BGP version that we're running, their autonomous system number, how many messages have been sent and received, what table version we're running. This does not have to deal with BGP v4. It's just basically how many updates we've received, and then how many prefixes we're learning from the peer. Now, we do want to see a number here. Even if that number is 0, it's better than seeing idle or active. Idle or active would indicate that there's some sort of issue with that particular peer. All right? So the router ID, the local autonomous system number, which in this case the router ID was derived from SP1's loopback interface, the table version number, that's going to increase each time that the database is changed, the BGP rib, if you will. In the second section here, we see the IP address of the neighbor, like I said, the BGP version number that's used by the peer when we're communicating. MPBGP would be another example where we might be running address family configuration, the number of messages, and so on, like I said. All right, and then finally, how long has the neighbor been in its current state, and how many prefixes have I received from that particular peer? So 1.11 is R1, that's an AS100. 2.11 is R2, that's an AS200. We can also use kind of the more robust output, show IP BGP neighbor. And this particular output provides a lot more information, quite a bit of detailed information. It tells us it's an external peer. This is the remote router's router ID. We definitely want to see that the BGP state is established, how long the BGP session has been active. Here's our keep alive interval. As I mentioned before, it's every 60 seconds. A lot of internet service providers will set that keep alive interval to 0, which means no keep alives, to identify the state of the BGP session, but they're going to use other methods for identifying whether or not a peer is up or down, something like BFD or something like that, right? We have one active neighbor session. We can see how many open messages. These are all the different BGP messages. Opens, of course, you shouldn't see those incrementing too much because those are only used to establish the session. You should definitely not see any notifications. Notifications are used in BGP to identify issues or errors. Updates probably shouldn't increment too much, but certainly each time that we have routing updates or policy changes and we do a soft reset on a peer or we change the BGP table, keep alives, these should definitely be incrementing and so on. So these are essentially the 6 different message types or 5 different message types that you would see: open, notification, update, keep alive, route refresh, and so on. All right. We can also see other detailed information about the peer. For example, the BGP table version number, the actual peering address, and we also have some capabilities exchange that happens here, and so on. That kind of gets outside of the scope of this class, but we do see lots and lots of detailed information about these particular peers. We can identify from this output here what is the TTL, who is the client and who is the server. In this case, the local port, which is me, 1.10. I am acting as the client using one of those ephemeral ports, 60,329, and 1.11 happens to be the server. That means that essentially I was the router that initiated the session, which kind of makes sense because SP1 was the first router that we booted up in this particular case. And was the router that we actually enabled BGP on manually, right? We see a whole bunch of other information here, and then we get into the next peer. All right, so lots and lots of detailed information in this case. All right, we do want to see a established session. We don't want to see idle or active in the summary output. Now, another thing that we can look at is the actual BGP rib, show IP BGP. We talked a little bit about the different BGP attributes and how path selection is done. We talked about the BGP table. We can see that there are 3 different prefixes here. One of the well-known mandatory attributes in BGP is the next hop. The metric, local preference, wait, Aas Path, these are all also not mandatory but well-known attributes. Wait is Cisco proprietary. Prefixes that I do not originate, that originate from somebody else, always have a default weight of 0. Prefixes that I originate have a weight of 32,768. The metric is that multi-exit discriminator value. That's going to have a default number of 0. Local preference is not set in this case. And the Aas Path. So this is a prefix that's coming from AS100. This is a prefix coming from AS200. And this is an internal path, an internal prefix, right? We also see here the asterisk and the greater than symbol. Asterisk indicates that it is a valid route. The greater than symbol would indicate that it's the best path. So we may have multiple paths to choose from, and only one of those paths is going to have the greater than symbol. Most of them might be valid, but only one is going to have a greater than symbol. Basically, the greater than symbol indicates that it's put into the global rib. All right. Now you might see a little R there. instead of a greater than symbol, you might see an R. R would indicate a rib failure. Rib failure would mean that the route would not go into the global routing table because perhaps the route is being learned by some other process that might have a lower administrative distance, like an IGP routing process, or there may be other reasons why a prefix might not be entered. All right? If the BGP table contains more than one route to the same destination, the alternate routes would be displayed in consecutive lines, right, under the same prefix. So I might have 3 or 4 or 5 paths to 10.0.1.0, and I might have 3 or 4 or 5 different entries. The path selection process, which we've talked about quite extensively, is going to be responsible for choosing a particular path based on that algorithm, the BGP best path selection algorithm, right? Weight, local preference, Aas Path, locally originated route, etc. All those different multi-exit discriminator and so on. All the different variables that are used in the path selection process. All right. So the metric, the column metric, local preference, weight, path. These are all factors that contribute to determining the best path. Now, in this case, we don't have alternate paths available, so we're not necessarily concerned too much about the path selection process because there are no tiebreakers in this particular case. We essentially only have one path for each destination. Now, if you look at router 1 here, the 10.0.1.0 prefix, the next hop is quad 0, which means that's a self-originated prefix. But for 10.0.2.0, notice the next hop attribute, right? The next hop attribute is the external peer. In this particular case, that works out perfectly because we have a hub and spoke environment. But if I was to then process this route to, say, another iBGP peer, I may have to modify that next hop attribute because the next hop attribute is not modified by default between iBGP peers. It is always modified between eBGP peers. All right? If I go back to SP1 and I do a show IP route, BGP, I can see the two prefixes, the two BGP prefixes. And notice the administrative distance is 20. For external BGP, it's 200 for internal BGP. And there is no metric, right? Because BGP doesn't really use a traditional metric when it's trying to determine how to reach a particular destination. So both customers are reachable. They're both reachable with a B in the routing table indicating that these routes are learned through the BGP process. We can, of course, test our reachability by simply pinging those loopback interfaces, which we know should work in this particular case. All right? So this is a really basic exercise. This is the extent of what they wanted to cover in the ENCOR discovery. Obviously, there are many other things that we could discuss in relation to BGP, but this was just kind of a basic discovery about peering with external BGP peers. When we get into the advanced routing section, we're going to spend quite a bit more time on different BGP attributes and how those BGP attributes are used to make routing decisions. So we'll talk about that in much more detail once we get into our routing lessons in the ENARSI course. All right, so we're going to go ahead and wrap up this discovery, very quick one, and we'll see you guys in the next section of this lesson. All right. So on to the summary challenge. By default, what is the valid AS number range for a BGP process on a Cisco router? 1 to 65,535. In the following output, the AS number is 65,200, and that is for which router? Well, this is the ASN for this peer. Whether or not it's also the ASN on this router, we can't really tell because we don't see the global routing command. But it is definitely the AS for 10.108.200.1. All right. We can't tell whether it's both routers or not because I don't see the router BGP command, so I can't really infer what the local AS is. Just because we see the word remote AS doesn't mean anything. A lot of people get confused about that because remote AS seems to give you the impression that it's an external peer, but we use the same syntax for internal peers as well. Which TCP port does BGP establish a session with? 179. Based on upon the given output, which statement correctly describes whether or not the BGP session is established between the peers? This one right here. We know it's not established because, like I said, and the columns are kind of messed up here again. This is the state and prefix column. So the state is active. If I was established, I wouldn't see state, I would see prefix received. So no, it is in the active state. We're still trying to establish a session. Make sense? All right. Which command will display how long a BGP pairing relationship has been up? Show IP BGP summary will show you that. In fact, we can go back up and see that. We can see it's cut off here, actually. Up down would show it. We have a 0 here. The formatting again is kind of messed up. Up down will show us that time that we're established. Let's see. Which character in the BGP table of routes indicates the best path? That is the greater than symbol. Asterisk just simply means that it's valid. What does the next hop of quad 0 indicate in this output? Show IP BGP. Quad 0 means that I'm the one that's originating the route. All right. So that means the network is locally originated via the network command in BGP. All right. So that concludes that lesson. We'll see you guys in the next lesson.